This video gives more examples of finding the equations of lines and planes. Let's start by finding the equation of a line through the point 3, -1, 2 that's perpendicular to the plane with this equation. Recall that the equation of a plane can be written in the form ax plus by plus cz equals d, where the three coefficients a, b, and c form a vector that's perpendicular to the plane. So for our plane, 4x minus 6y plus z equals 13, the vector 4, -6, 1 is perpendicular to this plane. Well, if we want a line that's perpendicular to the plane, then the line must be going in this direction. So I'll write the direction vector of the line is 4, -6, 1. And the point it goes through, or a point it goes through, is 3, -1, 2. So one way to write the equation for the line is to use parametric equations. X starts at the x value of 3, and every second it goes 4 units in the x direction, so we can write that as 3 plus 4t, where you think of t as time. Y starts at -1, and every second it goes -6 units in the y direction. And z starts at 2, and every second it goes 1 unit in the t direction. So here are parametric equations for our line. Of course, if we wanted to, we could also write the line using symmetric equations by isolating t in each equation and setting the t's equal to each other to get x minus 3 over 4 equals y plus 1 over 6 equals z minus 2. A third way of writing the equation for the line is using vector notation. xyz equals 3, -1, 2 plus 4, -6, 1 times t. The idea behind this vector notation is if I draw each of these vectors given here and put their tail at the origin, then the tips of these vectors will have x-coordinate given by 3 plus 4t, y-coordinate given by -1 minus 6t, and z-coordinate given by 2 plus 1t. So those x, y, and z coordinates of the tip of my arrows will be exactly the x, y, and z coordinates given by these equations. So those tips of the arrows will sweep out the line. As our next example, let's find the equation for the plane through these 3 points. Well, again, I know that I can write the general equation for a plane as ax plus by plus cz equals d, or I could write it in this form: a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0, where a, b, and c, again, is a vector perpendicular to the plane, and x naught, y naught, z naught is a point on the plane. So if we could just find this vector perpendicular to the plane, we'd be home free, because we could just write down this equation, because we've got plenty of points. We've got 3 points. We could pick one of them to plug in for x naught, y naught, z naught. We just need this normal vector. Well, I could find some vectors in the plane, and the key idea here is going to be taking the cross product. Once we find vectors in the plane, when we take the cross product, that automatically gives us a vector perpendicular to those vectors. So let's find vectors in the plane. If I call this point P, this one Q, and this one R, I could take, for example, PQ and PR. PQ will have components 5, 3, 2 by subtracting coordinates, and PR will have components -4, -1, -5. Now I will get my normal vector n that's perpendicular to the plane by taking the cross product. I'll write out my matrix. And I get that my I component is going to be 3 times negative 5 minus negative 1 times 2, minus my j component. And here goes 5 times negative 5 minus negative 4 times 2, plus my k. And here goes 5 times negative 1 minus negative 4 times 3. That simplifies to I times negative 13 plus j times 17 plus k times 7, or the vector minus 13, 17, 7. Now I can write down the equation for my plane. I'll use this first point for my x naught, y naught, z naught, but you could use either of the other 2 points and you'll get an equivalent equation. So I write down minus 13 times x minus 3 plus 17 times y plus 1, because it's minus minus 1, plus 7 times z minus 2 equals 0. I can distribute things out and simplify to get minus 13x plus 39 plus 17y plus 17 plus 7z minus 14 equals 0, which gives me minus 13x plus 17y plus 7z equals negative 42. Either one of these 2 equations, this one or this one, are perfectly fine as final answers. One is in the form of this equation and the other is in the form of that equation. And recall that the key idea that we used here was cross product. That's what allowed us to get a normal vector to the plane once we had 2 vectors within the plane. I want to make an analogy between lines in the plane and planes in space. What information is enough to determine the equation for a line in the plane? Well, typically we need a slope and an intercept, or just a slope and any one point will do. Or we could get the equation for a line in the plane just with any 2 points. First, we use the 2 points to get a slope, and then we use the slope and 1 point to write down the equation of the line. The situation for lines in 3-dimensional space is somewhat similar. We could, instead of the slope, doesn't really mean anything in 3D, instead we have a direction vector. So we could use a direction vector and 1 point. Or we could use any 2 points, because we can use them to get the direction vector. And then we're back to here. What about the equation of a plane in 3-dimensional space? Well, for the plane, we need the normal vector and a point. Kind of similar to how we need a direction vector and a point for a line in space or in the plane. But if we don't have that, we could just use 3 points, because we can use them to get 2 vectors in the plane, as we did in a previous example, and then take the cross product of these 2 vectors in the plane to get the normal vector. And then we're back to the first situation. There are other possibilities we can use to get the equation for a plane in 3-dimensional space also. For example, we could have a line in the plane and a point in the plane. One way, those also determine a plane, and one way to get the equation of the plane would be to use the line to get 2 points, and then we have 3 points, and we're in the previous situation. I should mention here that when we're talking about 3 points, they need to be not collinear. Otherwise, if they're collinear, that means all on a line, they won't determine a plane. And the point needs to not be on the line, so that that way the 3 points won't be collinear, and you'll determine a plane. So one other way you can get an equation of a plane sometimes is from two lines in the plane. And again, you could use this maybe to get 3 points. And then you're back to this situation. So anyway, anytime I'm asked to find the equation of a plane, I'm going to be looking around either for maybe I already have a normal vector and a point, and if I don't, I'm going to be looking for some way to find 3 points. Once I have 3 points, I know I'm home free. I can just use them to make two vectors, take the cross product, and I've got my normal vector. So these are sort of the key situations, and I think of every other situation as just a variant in which you can ultimately find 3 points and then a normal vector. In this video, we did some examples of finding equations of lines and planes, and we reviewed the information that's needed to find an equation of a line or a plane.